Hi, welcome to my channel, JaberTime. Today I'm going to go over graphs of polynomial functions. As you can see, I have a graph in detail, and we're going to talk about the multiplicity and the intermediate value theorem. Let's get into it. These two graphs describes polynomials. Polynomials are continuous and smooth. So the left one is a polynomial. This right here on the right is not a polynomial since it's discontinuous. Let's see more examples. I have 4 graphs right here, and it says which of the graphs shown represents a polynomial function. The graphs of f and h on the left are graphs of polynomial functions. They are smooth and continuous. That's kind of like the way we describe them. An easy way to describe them. Now let's look at these ones. They are a little bit different. These two are not polynomials, and here's the reasons. The graphs of g and k are graphs of functions that are not polynomials. The graph of the function g right here has a sharp corner. It's not a polynomial. This graph right here, the function k, is not continuous. So that's what we're talking about polynomials as graphs. Let's talk about graphical behavior of polynomials at x-intercepts, which is an interesting topic because in lower math we don't discuss that at all. We just look for the zeros where it crosses the x-axis, but it's more than that. If a polynomial contains a factor of the form x minus h to the power p, the behavior near the x-intercept, which is h right here, when you set this equal to 0, it's x equals h, is determined by the power p, how many times it repeats. We said that x equals h is a 0 of multiplicity p. The sum of multiplicities is the degree of the polynomial function. In lower math, when we factor, we say x equals 5 and we stop right there. But sometimes it's x equals 5 twice or 3 times. Like when you say x minus 5 as a factor to the power 2, that means x minus 5 times x minus 5. So the 5 repeats twice. That's what we don't discuss in lower math or algebra 1, let's call it. The graph will cross the x-axis at zeros with odd multiplicities. Now all this is not fully clear till we see some examples, which is coming soon, right after this. The graph will touch the x-axis at zeros with even multiplicities. So keep those in mind. I'm just mainly highlighting the keywords, which is cross and touch. For odd multiplicities, it's going to be crossing. For even multiplicities, it's going to be touching and bouncing off. Here's a graph when p equals 2, like x to the second somehow. This is not x to the second, but it looks like it to some degree. 0 with multiplicity of 2. So it touches and goes up. This one here, p equals 1. That's a linear, a straight line, horizontal, a straight line. It's gonna cross. When p equals 3, it does cross, but it flattens near the 0. 0 with a multiplicity of 3. Here's more detail in writing. The zeros with even multiplicities will touch or are tangent to the x-axis. It looks like it's a tangent. If you zoom in a lot right here, you'll see it like it's a tangent. For higher even powers, like when you go x to the second, x to the fourth, x to the 12, and so on, this is what's going to happen. As 4, 6, and 8, the graph will still touch and bounce off the horizontal axis. In this case, it's the x-axis. But for each increasing even power, the graph will appear flatter as it approaches and leaves the x-axis. So right here, it's going to be like getting too close and almost going with it, as like almost touching it more than once, and goes back up. The zeros with odd multiplicities like 1, 3, 5, and 7 will cross. This is crossing to the other side. This is crossing to the other side, or intersects the x-axis. Same idea. For higher odd powers, such as 5, 7, and 9, the graph will still cross through the horizontal axis, but for each increasing odd power, the graph will appear flatter. As you can see here, it's flat, almost. This is like x cubed, but imagine if you take it as x to the 7th. It's gonna be even, almost touching it more than once. It looks like, but it's not. So it's gonna be flatter. Sketch the graph of f of x equals x to the 6 minus 3x to the 4 plus 2x to the 2nd. To find the zeros, we need to find the solutions to f of x equals 0. So we need to set this equal to 0. Hopefully we could factor it, and we move on. So x to the second 6 minus 3x to the 4 plus 2x to the 2nd equals 0. That means I need my y to be 0, because as x-intercepts, y should be 0. Factor out the greatest common factor, with factoring skills that we have. Here they all have x, and actually x to the 2nd I could take out as a greatest common factor. So we'll take it out. And the rest, as you could see, stays inside. There is no point to read it. It just like mainly focus on the idea and the concepts, so I could move on and save you some time instead of making it a lengthy video. Now, the inside part is a trinomial, 3 terms. We could still factor it, but take a look. X to the 4th minus 3x to the 2nd plus 2, it's actually something like this. X to the 2nd to the 2nd minus 3x to the 2nd plus 2. So it's almost like a to the 2nd minus 3a plus 2. So I could still factor it this way. X to the 2nd minus 1 and x to the 2nd minus 2. So when you multiply minus 1 times minus 2, that's positive 2. When you look the inner terms and the outer ones from the word FOIL, I have minus x to the 2nd, and I have minus 2x to the 2nd, which is minus 3x to the 2nd. And if you multiply the front ones, you get x to the 4. All right. Now we set this equal to 0, which means I have 3 factors. The principle of zero products becomes handy. And we set each factor equal to 0, just like this. This will give you, usually in lower math we just write x equals 0. But in this time I'm going to write x equals 0, comma x equals 0. Because it's called actually a repeated root. This one here, when you move the 1, take the square root plus minus 1, move the 2 plus minus square root of 2. So this is something we don't do, as I said, in lower math. Or in short, we say x equals 0 is a 0 of multiplicity 2. We have 5 x-intercepts, 0, 0, negative 1, 0, 1, 0, negative rad 2, 0, and rad 2, 0. This is what we're learning from this problem. The 0 is a multiplicity of 2. And we talked about that the even zeros with power with multiplicity of p that is even, it's gonna touch the x-axis. We talked about that. I don't want to take you all the way back, but let's take a look. You see at 0, first of all, this is to the power 6, so it's even. And this is even function. Even means opens up from both sides, or opens down and reaches down to negative infinity on both ends. We talked about that in the last video in behavior model. Now, because the leading coefficient is positive, so it's going to open up both sides, if it's even. If it's odd, it's going to go like down and up, or the other way around. It's going to cross at negative rad 2. It's going to cross at negative 1. It's going to bounce. Since I went down, back up, then back down, I am on top. So once I reach to the 0, 0, which is actually a y-intercept and an x-intercept at this time, it's going to bounce off. This is something new. All right? Just keep it in mind. Goes back and on. Since it's symmetric, you could double check negative and positive. That's going to give you the same thing on the right and left. Symmetric above the y-axis, we call it even. So now you have it. Multiplicity of 2, the root or the 0, x equals 0, has a multiplicity of 2. Graphically, it touches and bounces off. Here's another graph. Use the graph of the function of degree 6. They told me it's a degree 6. To identify the zeros of the function and their possible multiplicities. All right. The polynomial function is of degree 6, what we were told that. The sum of the multiplicities must be 6. Since now we don't call x equals 0 like the previous problem as 1, 0, we call it 2 zeros. Now we have all the zeros. We count them all, and they should add up to the degree of the polynomial. So, one by one. At x equals negative 3, right here, take a look. The graph touches the x-axis, so the multiplicity of the 0 must be even. The 0 of negative 3 most likely has a multiplicity of 2. Now we could fix that if we need to, but that's most likely bounces off normally. Of course, we want to keep in mind that the degree is 6. At negative 1, right there, it crosses. The graph looks almost linear at this point. This is a single 0 of multiplicity 1. At 4, it flattens, as you can see, right? You see that? It's different than this guy. The graph crosses the x-axis, so the multiplicity of the 0 must be odd. We know that the multiplicity is likely 3 because it flattens. It's not 1. 1 is going to cross like this, just crossing. And because that 3 and 1 and 2 will add up to 6. And the sum of the multiplicities is likely 6. So we pick on 3 on this one instead of 1, or even 5. Okay? That should do it for this problem. Let's see another one. Sketch the graph of f of x equals negative 2 multiplied by x plus 3 to the second times x minus 5. This one is given to me already factored, so we could save some time from factoring. I could talk about this in a lot of different ways. I just want to stay focused with the notes, and I have enough notes for you, so let's get into it. The graph has two x-intercepts, one from here and one from here. The first one is x equals negative 3. At x equals negative 3, the factor is squared, indicating a multiplicity of 2. So we do have a multiplicity of 2 for the 0, negative 3. And you know what that means? It's going to bounce at negative 3. Let's keep that in mind. So the graph will bounce, as I mentioned. At x equals 5, it's a multiplicity of 1. The function has a multiplicity of 1, indicating the graph will cross through the x-axis at this intercept. So this one, if we're coming down, we're going to bounce down this way. If we're coming from the top, we're going to come and go back up. This one here, you cross either way or this way. We'll see how it's going to go. Let's find the y-intercept. To find the y-intercept, you set x equals 0, f of 0. Just plug in 0 for x, do the math, and I have 90. So it's going to cross at 0, 90, or 90 on the y-axis. Compared to the scale negative 3 and 5, this is like a little bit high. but that's what we have. Now, if you attempt to multiply this and make it standard form, you don't have to, but let's look at the leading term, because the leading term also tells us a lot. This has an x, this has an x to the second. If you multiply it, x times x to the second will give me x to the third, with a minus 2 up front, so the leading term is minus 2x to the third. That means it's a cubic. Cubic at the ends, or relating cubic to the x cube, pure 1x cube, it goes up through the origin and goes up this way. So it starts in the third quadrant and keeps increasing, let's say, and ends up in the first quadrant all the way up. Because of negative, it's going to be reflected about the x-axis vertically. So this part right here is going to be up, and this part here is going to be down. So in general, for this right here cubic, at the end, from the right and the left, that's how it's going to look like, and that's how it's going to look like. It's like I'm coming down here, and at the end I'm going to go down here. Now I'm not going to cross the x-axis once because it has enough terms, so it might give me more 1 or 2 or 3 zeros. We already know the zeros. I just want to give you an idea. So if it doesn't have other terms, it's going to go down this way. But if it has more terms, that means you have zeros. We'll see how it's going to go. At the end is what we care about. So it's going to start in the second quadrant. It's going to end up in the fourth quadrant. Now, all what I talked about, for your convenience, I have it written right here, and here, and one more here, telling you that it's not an even function, it's an odd function. It does not have symmetry about the y-axis. I covered everything, but if you want to read this, you could pause the video by hitting the spacebar and continue by hitting the spacebar again. I want to save some time from reading it because I just talked about the graph and the behavior at the end. It's called end behavior. So this is my expectation to the graph. With this as a double root or multiplicity of 2 single root crosses, Y-intercept, I believe the graph agrees and looks like this. Comes down, bounces at -3, crosses the y-axis at 90, turns back to cross at 5 and goes all the way down. That should do it for this example. Let's talk about the intermediate value theorem. The intermediate value theorem, IVT, is a common sense. I mean, some theorems we want to go deep to understand it, but this one is pretty much like it's common sense. Why? It says clearly, let f be a polynomial function, meaning smooth and continuous graphically. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of c equals 0. What does that mean? Here's f of a is negative, like whatever a is. A could be 2. And f of b is positive, whatever b is, maybe 3.2. Up here, that's a f of b. So if you are at some location down below the x-axis, negative value, and once you pass or move to the right a little bit, you are having positive values. So you are above the y-axis, the x-axis. What the mean value theorem says, there is no way that you could go from negative to positive without crossing the x-axis at least once. Because think about it, like if you are here and you want to go up here continuously, you could go up this way and cross the x-axis once. Or you could go up and down, back up, down, then change your mind and go up, continuing going up. That means you have at least 1 0, you could have more than one. Makes sense, right? If you are above and now below, there is no way that you could jump, since the polynomial are smooth and continuous. So you have to cross the x-axis to go to the other side. Let's see an example just to enhance it and make it clear. Show that the function f of x equals x cubed minus 5x to the second plus 3x plus 6 has at least two real zeros between 1 and 4. Well, to do that, this is a simple example. We're gonna just focus on this interval from 1 to 4. As a start, evaluate f of x at the integer values 1, 2, 3, and 4. And if you take your time and make a small table like this one, I could see already a 0 right here, because f of 2 is 0. That means it crosses the x-axis at 2. So 1 is done. When it says at least 2, let's find the other one. It's right here. That's why I'm boxing it for you. At 3, you are below the x-axis at -3. Once you go to 4, you are above the x-axis. There is no way that you could jump from below to being above without crossing the x-axis between 3 and 4. So we see that 1, 0 occurs at x equals 2. Since f of 3 is negative right here, and f of 4 is positive, by the intermediate value theorem, there must be at least one real zero between 3 and 4. Now you have it. 1 is at 2 exact, and 1 lives between 3 and 4. We have shown that there are at least two real zeros between 1 and 4, answering the question. They're not asking me exactly what are they to display the roots. This is just show that there are at least. So we did. One, we found it exact, and the other one lives between 3 and 4. That should do it for this video. Thank you, and I'll see you in the next one. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.